Hello everyone, my name is Kiera Davis and today I'm going to be talking about enzymes and proteins from extreme thermophils. First, what are extremophils? Extremophils are microorganisms that are adapted to very hot temperatures and high pressure, living, thriving, growing best between 70 and 100 degrees Celsius. They're usually found in hot springs or hydrothermal vents, and these microorganisms are primarily prokaryotic, either archaea or bacteria. They can also be referred to as obligate thermophils. In this picture to the left, Thermococcus littoralis is a bacteria that resides and grows in hydrothermal vents, as well as the Pyrococcus furiosus, which is on the bottom right of the screen. Why are they important to society? Extreme thermophils can be used for biodegrading and bioremediation purposes in extreme environments. They are sources to biofuel and bioenergy, and in the future they serve big purposes that are crucial to accomplish targets of sustainability and bio-based economy. In the image on the left is the before and the right is the after pictures of bioremediation. On the left you can tell that it's very dirty, a bunch of trash, microorganisms, bacteria, just dirtiness. And on the left or on the right is the after pictures, and you can tell it's luscious, everything's grown back out, it's not dirty, and this is due to bioremediation. Enzymes from extreme thermophils. Enzymes from extreme thermophils can work under conditions that normally would denature mesophilic enzymes. Mesophilic enzymes are enzymes that only survive between 20 and 40 degrees Celsius and cannot withstand the heat that extremophils can. Conventional enzymes from extremophils have great thermostability, meaning they are not easily destroyed by heat, and enhanced activity when in the presence of common protein denaturants. These denaturants include things such as detergents, organic solvents, and proteolytic enzymes, also known as protease, which breaks down proteins into smaller peptides, polypeptides. Advantages of thermally stable enzymes include the production of high fructose corn syrup and cellulose and hemicellulose hydrosis, which is important when processing renewable resources. On this slide shows 9 graphs. The top 6 in blue are mesophils, and the bottom 6 in red are extremophils. On the y-axis is the growth rate, on the x is the temperature, and as you can see, mesophils do not have a high growth rate within high temperatures. They cannot go and grow and survive in higher temperatures, unlike the extremophils in the red do. Why are enzymes from extreme thermophils important to society? These enzymes have a considerable amount of recognition from the industries because of their specialized characteristics like high stability and to changes in pH. They are being targeted for the suitability while investigating protein thermostability and the potential as biocatalytics in modern biotechnology. Enzyme molecules have a good amount of potential in the industrial field because of their ability to get better yields under harsh operational conditions, which wouldn't be able to happen if you didn't have these extremophils that can withstand these high temperatures. They are important environmentally due to their biodegradability, stability under extreme conditions, use of raw materials, and the lower amounts of waste products. Continuing many industries in microbial analytic enzymes in the enzymic conversion of starch to sugar solutions. Polonase, a hydrolytic enzyme, is used with saccharifying amylase to improve production of different sugar syrups. Bioprocessing of starch into malto-oligosaccharides is gaining huge importance in the potential use in food, pharmaceutical, and the chemistry industry. Thermostable and thermoactive amylases also have a high value to society in the food industry because of the bioprocessing of starch at high temperatures. This improves the solubility in starch, decreases its viscosity, limits microbial contamination, and reduces reaction times. Proteins from extreme thermophils. Proteins from these extreme thermophils adapt to high temperature environments by means of mutations, which enhances conformational stability. For proteins to function under extreme conditions, multiple structure deliberations must be accommodated to balance activity, flexibility, and stability. Archaic proteins tend to be more compact due to tighter packaging, while extremophile bacteria are stabilized by salt bridges. These salt bridges produce bigger enhancements in protein stability at elevated temperatures. Protein adaptations are not necessarily uniform throughout all their proteins, making it harder, not as easy for researchers and scientists to study protein adaptation within these extremophiles. Variability in adaptations have been recorded multiple times throughout many studies of these proteins. Ideas I have listed below have been presented of why there are these differences in these thermophile proteins. First, they have presented that by only having a few protein modifications, the enzyme might have activity over a range of conditions. They also have presented that organisms have some flexibility to grow in a range of different conditions, and having various protein adaptations could be an alternative to regulatory pathways. However, they are not sure why there are these differences, but it is an ongoing research and for these scientists and researchers. Here's my references. That is it. I will be happy to answer any questions you'll have for me. Thank you.